Today we are treating motion under gravity. Under this topic, we are going to be considering upward motion of objects and free fall, that's downward motion of objects under the influence of gravity. We'll also consider motion of objects in lifts and elevators, and of course, movement along an inclined plane. At the end of the class, we'll take examples on the key areas we are going to consider, and questions will be given as exercise for you to test your understanding of the topic. Motion under gravity. Objects which are projected vertically upwards and objects or bodies falling from a given height travel under the influence of gravity. They travel at a constant acceleration called acceleration due to gravity, represented by small letter g, which is approximately equal to 10 meters per second square. For upward motion, the velocity of the object reduces uniformly with time. This is uniformly retarded motion. Such movement is represented graphically by this velocity time graph showing uniform retardation. The following equations are used for solving problems involving upward projection of objects. Number 1, V equal to U minus GT. H equal to U plus V divided by 2 times T. H equal to UT minus half GT squared. V squared equal to U squared minus 2GH. For downward motion under gravity, the velocity of the object increases uniformly with time. The graph is shown, graph of velocity against time. The following equations are used for solving problems involving downward motion, otherwise called free fall, of objects. These are V equal to U plus GT, H equal to U plus V over 2 times T, H equal to UT plus half of AT squared, V squared equal to U squared plus 2GH. Motion in a lift. For motion in a lift or elevator, let's work on the assumption that there is this person A inside the lift. The tension on the cable is represented by T, and the weight of the person inside, weight is mg. If the lift accelerates upwards, then the resultant force is equal to tension minus the weight. That means tension is greater than the weight. So the resultant force is MA, and this is equal to tension minus mg. Therefore, the tension is equal to the product of the resultant force, and the weight of the body. If the lift accelerates downwards, then resultant force F equal to the weight minus the tension. The resultant force is mass times acceleration. The weight is mg, then minus T for tension. Of course, when you make the tension the subject, you now have T equal to mg minus ma. Next are examples. The following are examples on the topic we've treated so far. Example 1. The body falls freely under gravity from a height of 40 meters onto the top of a platform 0.8 meters above the ground. Find its velocity on reaching the platform. Take acceleration due to gravity g to be 10 meters per second squared. Option A, 20 meters per second. Option B, 28 meters per second. Option C, 32 meters per second. Option D, 39.2 meters per second. The solution to this problem is obtained following the steps below. The actual depth covered by the falling object is 40 minus 0.8 meters. This is 39.2 meters. Initial speed 0, it fell from rest. We are also given the acceleration due to gravity as 10 meters per second squared. We are looking for the final speed. Using the equation for free fall, v squared equal to u squared plus 2gh. V squared will give us 0 squared plus 2 times 10 times 39.2. V squared will give us 0 plus 784. The final speed will give us square root of 784, which is 28 meters per second. By this solution, the right option is B. Option B is correct. Example 2. An elevator of mass 4,800 kg is supported by a cable which can safely withstand a maximum tension of 60,000 Newton. The maximum upward acceleration the elevator can have is dash. Option A, 2.5 meters per second squared. Option B, 5.0 meters per second squared. Option C, 7.5 meters per second squared. And option D, 10.0 meters per second squared. Example 3. We have an object that is hung on an inclined plane, a plane inclined at angle 30. Two masses, 20 kg and 30 kg. The tensions are as indicated by letter T. By the diagram, the object accelerates downward. The question is the acceleration of the system is what? We are asked to find the acceleration of the system above. The options are A, 2 meters per second square, B, 4 meters per second square, C, 6 meters per second square, and D, 8 meters per second square. The solution to the problem above is as follows. Solution. If the 30 kilogram mass accelerates downward the 20 kilogram mass will accelerate upward. So we take the case of the 20 kilogram mass first. Resultant force on it, resultant force is equal to the tension minus mg sine theta, the force acting along the plane. And the resultant force is ma, T tension minus mg sine theta. We fix the values. We have 20 times A is equal to tension minus 20 times 10 sine 30. 20A is tension minus 200 times 0.5. 20A equals to tension minus 100. Tension equal to 20A plus 100. I'll take this as equation 1. For the 30 kilogram mass, since it accelerates downward, the weight is greater than the tension on this rope. Weight is greater than the tension T. Resultant force on it is the weight minus the tension. The resultant force is mass times acceleration. The weight is mg minus the tension. Thus, we have 30A is equal to 30 times 10 minus T. 30A is equal to 300 minus T. T will give us 300 minus 30A as our equation 2. Comparing equations 1 and 2, equations 1 and 2 above, we have 20A plus 100 is the same thing as 300 minus 30A. 20A plus 30A is 300 minus 100. 50A is 200. A is equal to 200 over 50, which is 4 meters per second square. The correct option is B.